So as we briefly talked about last time, simplifying digital logic circuits is one of the most important skills that an electrical or computer engineer can have if he or she is working in the digital industry. Now, we can look at a number of ways to do this simplification, and I promise that in just a couple of weeks, I'm going to give you a new tool that's going to be really powerful for simplifying these circuits. But for now, the tools that we have are Boolean algebra, perfect induction, and Venn diagrams. And if I'm being honest with you, it's really Boolean algebra. That's really the tool that's going to be the most useful for us and the most powerful. So let's look at an example of how we could simplify a circuit. Now, let me just take a minute here and observe that this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 gates to it. This is by far the most complicated circuit that we've seen so far. It also has W, X, Y, and Z. It has 4 inputs. So it's a pretty complicated circuit. The question is, if we were being employed as an electrical or computer engineer, could we simplify this circuit? Could we reduce it down? Well, the answer is yes, or else I wouldn't be showing you this example, but I think you'll be astounded by how much we can simplify the circuit. Now, the first thing we can do is we can identify the Boolean function that is being implemented by that circuit, and I'll leave it to you to be able to derive that this is it. But you can see, for example, W and 1, X and not X, those are ORed together. X and Y is ORed with X. So you can see that this function can be generated directly really from the circuit diagram. And now we're gonna really just focus on the function. So once we have the function, now it's time to do a little bit of work about reducing the function, doing some Boolean algebra. So for example, X and not X, as we've seen repeatedly, X and not X is just equal to 0. W and 1. If you go back and look in the lesson about Boolean algebra, you'll see that one of the things is that if you AND anything with 1, you get that thing back again. So this really just becomes W or 0. So W or 0 goes right there. That's ANDed with X or X and Y. Now I'm going to put an X and 1 here. I could actually just look at the properties and the theorems and see that X or X and Y actually reduces down to X. But I'm kind of trying to show you the full method here. So I'm ANDing it with 1, and then I'm going to factor an X out of both of these two terms so that I get X and the quantity 1 or Y. Looking over here, I have X and Z or X and not Z. Well, I can factor an X out of both of those two terms. And then when I have Z or not Z, it's like say, hey, show me everything that is a monkey and also show me everything that is not a monkey. Well, that would be the whole universe. The whole universe is either a monkey or not a monkey. And so we've got Z or not Z just reduces down to 1. So X and 1, and then this is X and the quantity 1 or Y. Well, 1 or Y just reduces down to X. By the way, W or 0 reduced down to W. So I have X and 1 or X and 1. Both of those two terms are going to reduce down to just X. And then X or X reduces down to just X. So in the end, this function, which was big and massive up here, which involved 12 digital logic gates and 4 variables, reduces down to just a single AND gate. It reduces down to just W and X. And figure 7 and figure 8, the big massive circuit and the simple little AND gate, are 100% equivalent. Absent any sort of advanced tools, you'd be really, I don't know that you could tell the difference of the output coming out of those two circuits. And if you could tell a difference, the second one would be preferable. So for example, you might find that the second one would operate more quickly. It might operate at a higher frequency. Regardless, when you simplify, you always make the circuit better. You make it take less area, you make it take less money, you make it take less silicon, you make it have a higher reliability in its construction, you make it operate more quickly. Everything gets better when you simplify the circuit. So here you can see this is how we simplified the circuit using just Boolean algebra. Also notice that 2 of the 4 variables were completely irrelevant. We didn't even, in the end, we don't even care about what Y and Z are. The output is completely independent of Y and Z. Sometimes that happens in digital functions, and it's always good if you can identify that to be the case. Now, most circuits are definitely not going to simplify so dramatically. This one was cooked to make it so that it would reduce quite well down from 12 gates down to just 1. But many designs can be simplified at least a little bit. So if you were to look at a circuit and if you were to spend an hour trying to minimize that circuit or reduce that circuit, and if that could save your employer 1 penny for each chip that's being built, imagine if you're going to make 1 million of those, that's $10,000 that your company just earned from 1 hour of your work. If you can save your company $10,000 for an hour of your work, that's always an hour that was well invested. So now it's time for you to solve the digital logic simplification example problem. Then come back and we'll talk a little bit about universal gates.